For 40 years, scientists have been on a ghost hunt. A ghost that makes up a quarter of our entire universe. That literally holds galaxies together, and yet it's completely invisible. So today, we're going to dive into the epic 40-year search for dark matter and ask why, after all this time, we've still found, well, nothing.
Our story starts with a pretty humbling realization. We used to think we were the center of everything, right? Then we found out we're on a tiny little planet orbiting a pretty average star in a totally normal galaxy. But it turns out the ultimate cosmic punchline is this. The very stuff that we're made of, it's not even the main ingredient in the universe. Not even close.
And this is what the physicist Bernard Sedulek called the ultimate Copernican revolution. Just think about that for a second. Not only are we not at the center of the universe, we're not even made of what the universe is mostly made of. Everything we see, everything we are, we're just cosmic foam on top of a vast, dark ocean. This chart right here really lays out our cosmic ignorance. So everything we can see and touch, all the stars, the galaxies, you and me, that all adds up to a tiny 5% of the universe. Then you've got this huge chunk, about 25%, that's something else entirely, dark matter. We can't see it, we can't touch it, but we know it's there. We can see its gravity pulling on entire galaxies, holding them together.
Okay, so for decades, the prime suspect for what this stuff could be was a particle called a WIMP. That's a weakly interacting massive particle. And the theory behind it? It was just so elegant, almost too perfect. Physicists figured out that if a particle like a WIMP existed in the super-hot, dense early universe, then the laws of physics would have naturally cooked up just the right amount to explain all the dark matter we see today. This became known as the WIMP miracle. And just like that, the hunt was on.
But how do you actually hunt for a particle that's basically a ghost? I mean, something that can pass right through you, through the entire Earth without leaving a trace? Well, the answer is you do it with a ton of patience, some incredible ingenuity, and yeah, a little bit of luck.
And the progress, it's just been mind-blowing. Take a look at this. On the left, you've got data from one of the very first experiments back in 1992, using a little crystal detector no bigger than your fist. On the right, that's a peek at the massive, incredibly complex detectors we're building today. It's like we've gone from trying to hear a whisper in a quiet room to trying to hear a pin drop in the middle of a hurricane.
Science is funny. Sometimes the biggest leaps forward happen completely by accident. One of the biggest breakthroughs in this whole search came from a happy accident. Back in 1989, a student did some, let's call it creative wiring on a detector, and accidentally made it possible to measure two signals at once, the heat and the electrical charge from a particle hitting it. And this was a total game changer, because it gave scientists a way to filter out all the background noise and zero in on the signals that might actually be dark matter. Now the thing is, when you're looking for such a tiny, faint signal, it's really easy to fool yourself, to see what you want to see. So to get around that, the community came up with this brilliant technique, blind analysis. Scientists would literally hide the real data from themselves while they were building their analysis. They'd even salt the data, secretly adding fake signals to make sure their software could find them. Only at the very end, when everything was locked in, would they open the box and look at the real data for the first time.
So, you'd think a hunt this intense would be super cutthroat, right? And yeah, it was. But what's amazing is that it also created this incredibly open, collaborative community. Competing teams would actually share their methods, they'd check each other's results. They called it competing with open books. As one physicist famously said, through it all, they managed to stay friends.
But here's the thing. After all that incredible work, the universe just wasn't talking. The WIMP was nowhere to be found. And instead of finding dark matter, the experiment started getting haunted by these ghosts in the machine. Tantalizing signals that looked like a discovery, but would just vanish or just couldn't be explained. Okay, so one of the biggest headaches is this weird background noise. See, as the detectors get more and more sensitive, they start picking up more and more random chatter from the universe. And right down at the low energies where you might expect to see a light dark matter particle, this background chatter can become this deafening roar, completely drowning out the real signal. And one of these phantom signals is something they call a heat-only event. These are basically little bursts of heat that pop up in the detector, but they don't have the matching electrical signal you'd expect from a WIMP. Right now, the leading idea is that it could be caused by something as boring as tiny little cracks forming in the detector material itself.
It's this constant battle to hunt down and kill these instrumental ghosts that can perfectly mimic a discovery. And that brings us to the DAMA experiment in Italy, which is probably one of the longest, most heated controversies in modern physics. For over 20 years, the DAMA team has been reporting a signal that seems to get stronger and weaker with the seasons, which is exactly what you'd expect if the Earth was flying through a big cloud of dark matter. And the statistical significance of their signal? It's a mind-boggling 8.9 sigma.
Okay, so what on earth does 8.9 sigma even mean? Well, in particle physics, 5 sigma is kind of the gold standard for claiming a discovery. An 8.9 sigma result is just, it's off the charts. The odds of that happening by random chance are less than 1 in a trillion. So you'd think, case closed, right? Well, not so fast, because the rule in science is extraordinary claims require extraordinary evidence. And so far, not a single other experiment on the planet has been able to see what DAMA is seeing, which leads most physicists to believe it's got to be something else.
So all of this long and, let's be honest, fruitless search has really forced some soul-searching in the physics community. Now the question isn't just how do we build a better detector? The bigger question is, in a search for something we don't even know what it is, how do we define what a discovery even looks like?
And look, the hunt is absolutely not over. The next generation of experiments, like this one called Tesseract, are being designed to be way more flexible. The idea here is to use a bunch of different detector materials. That way, they can hunt for a much wider range of particles. And, this is key, they can help nail down and eliminate those instrumental ghosts that have been confusing the picture for so long.
And this all leads to a really deep question, one that goes way beyond just the data. It's something physicist Dan Hooper has asked. In a field where we're looking for something that we don't even know the properties of, how do we all agree that we've actually found the thing? You've probably heard about this 5 sigma rule for discoveries, right? It's famous. It's a really high bar that's meant to stop scientists from getting fooled by random statistical blips. But here's the thing, it's not some ironclad law. Back in 2016, the Large Hadron Collider saw a hint of a new particle at 4.6 sigma. It caused a huge stir. Something like 500 papers were written about it. And then, poof, more data came in and it just vanished.
There's actually a more powerful way to think about all this, and it's called Bayesian inference. Think of it like this. If you're a detective, you don't just look at a clue in isolation. You weigh it against how likely your suspect was to have left that clue in the first place. That's Bayesian thinking. It combines the new evidence with what you already believe. And in physics, that's called the theoretical prior. It forces you to ask, how likely was this theory in the first place? Let me give you a real-world example. A few years ago, there was a signal from the center of our galaxy that looked a bit like a certain kind of WIMP. So physicist Dan Hooper actually sat down and calculated his own prior for that theory. Before looking at the data, just based on his own knowledge of physics, he figured there was only about a 5.6% chance that this specific theory was the right one. Now that number isn't some objective truth. It's his way of putting a number on his own scientific gut feeling.
You can think of it like a Drake equation for dark matter. The point isn't to get the exact right answer. It's to break this massive, fuzzy question down into smaller pieces and make our own biases explicit. And this way of thinking, it really helps explain why a discovery like the Higgs boson, which was predicted for decades, was accepted almost overnight, while other, weirder signals get met with a whole lot of skepticism, no matter how strong the statistics look.
So what does all this mean? It means the discovery isn't just about hitting some magic number on a chart. It's a messy human process of building agreement, of weighing evidence against our own expectations, and of slowly, carefully convincing ourselves and everyone else that we've really stumbled onto something new about the universe.
So here we are. After a 40-year ghost hunt, the search for dark matter has become something deeper. It's a story about our unstoppable need to understand the cosmos for sure, but it's also a pretty humbling lesson about the limits of what we know. And it leaves us with this really provocative question. In a search for something you can't even define, how do you know when you're done? Or maybe the search itself is the point.